Welcome to the 7th video on block diagrams. This video is looking at nested loops. So far, the videos have developed rules for simple block diagrams, so those with a single feedback path, but possibly several blocks and loop inputs. We now want to look at block diagrams which have more than one feedback path, and this could happen, for example, in cascade control. Our intention is to use only simple approaches, and simple loop structures. Rules and shortcuts for more advanced structures are beyond the remit of this video. So what are we going to do? We're going to use some very simple methods which basically are focused around grouping together blocks where this offers simplification. So the main idea is to say, are there blocks I can group together and therefore make the underlying diagram look easier? So first what you do is decide which internal signal you're particularly interested in. So if you're trying to find the transference from a loop input to an internal signal, identify that signal and then look at which blocks you can group together to make the resulting diagram a bit simpler. Now this grouping will minimize the apparent complexity and make life easier. What we're going to do now is we'll go through an example using a long-winded method without grouping, and then we'll show how using shortcuts and grouping can make life easier. So here we go. Here's the first example. You can see there's two feedback paths. There's a feedback path here and there's a feedback path here. But what I should note is that both those feedback paths contain the signal Y. So they're feeding back the same signal. Now that's often the case, though not always. So let's go and look at the sort of long-winded method which we started with when doing block diagrams. So we write down the equations at every summing junction and around every block. So here we go. We've got E equals R minus Y, that's the first summing junction, and F equals U minus Y, that's the second summing junction. I'll put down F there so you can see where it is. And then you've got the two blocks, U equals ME and Y equals GF. So now all I need to do is solve these four equations as simultaneous ones. So here we go. The first thing I'm going to do is take U equals ME and rewrite it as U equals MR minus Y, substituting in for E. And then I take the equation F equals U minus Y and substitute in what I've just got for U. So now F equals M into R minus Y. And then I use the last equation, Y equals GF, put this F in, and so I get Y equals G into open brackets M R minus Y minus Y. Now, if I take all the Y's onto the same side and rearrange, you will see I end up with this expression here. Y equals GM over 1 plus GM plus G times R. So this expression is somewhat more involved than the denominators you've had in previous videos, and that's because we've got two feedback paths. And the key thing is, we'd say to you, please don't assume that you can spot the denominator by inspection, certainly not unless you're very experienced, because it may not be immediately obvious what this denominator should be. So now what we're going to do is tackle the same problem but using more of a shortcut method. And what this says is first re-sketch the plot or the block diagram so that you can reveal an underlying structure which makes it easier to solve. Now you might not think there's anything obvious here, but when I put this next diagram up, hopefully you will see what we've done. So I'll put in my signal F, not that we need it. Now the key thing was both feedback paths were returning Y, and therefore if you look at this new diagram you can still see that I've got Y on both feedback paths, but what I've done is I've given them both what appear to be separate loops or entirely separate loops, so it reveals a structure. I seem to have, I'll use a red line here, a sort of inner loop, here it is, and then an outer loop which in some sense appear to be decoupled. So what I can do next is I can take this inner loop which I've used with a red line and rewrite it as a different expression. So here we go. That inner loop can be represented as G over 1 plus G. And now you'll note that the loop structure that I've got has only one feedback path. And it looks like a standard loop structure which we've solved many times. We've got m in the forward path and g over 1 plus g in the forward path. Now you know that g over 1 plus g hides the level of complexity, but we don't need that if all we're trying to get is the relationship between, for example, r and y or r and u. So here we go. This is the loop structure that we've identified, and if I want to find the transfer function from r to y, I can now use forward path over 1 plus loop transfer function. And so what you will get is y equals, and I'm going to use a big box here, multiply this into r. So first of all, what's the loop transfer function? The loop transfer function is mg over 1 plus g. And the forward path is mg over 1 plus g. Now what I can do is I can multiply n now out by this 1 plus g, and what you will get is mg over 1 plus g plus mg. Okay? And so there you can see I've got the same answer as 2 slides ago for the transference between r and y. It's mg over 1 plus g plus mg. Now just as an aside, because we've got just about enough space on this page, what happens if you wanted to find the transference from r to u? Well, I could use the same type of rule and I would get u equals m over 1 plus mg over 1 plus g times r. And if I now multiply top and bottom by this 1 plus g, you would get m1 plus gr over 1 plus g plus mg. And again you see that the resulting expression is not immediately obvious, and so you do need to go through this analysis to work it out. However, key message, by grouping one of these feedback paths and creating a block g over 1 plus g, I've then been able to write down the transferences by inspection, albeit I need a little bit of algebra afterwards to get them into a simpler form. So here's another example. What do we do if I want the transference from r to y for this loop here? You'll see again there's 2 feedback paths, but one of the feedback paths has got a block in it. Now what I'm going to do is simplify this by grouping this particular inner loop, so the loop that's got h and g in it. So I'm going to redraw the diagram. So here we go, I've got r coming in, and then I go through m, and then this inner loop can be approximated as g, not approximated, it's exactly g over 1 plus gh. And now again you'll see I've come up with a loop diagram that looks a lot simpler. So now if I want to identify the dependence of y on r, I can just write down y equals gm over 1 plus gh all over 1 plus gm over 1 plus gh into r. And if you multiply that out by 1 plus gh, top and bottom, you will get gm divided by 1 plus gh plus gm into r. And again you will see that the denominator is not immediately obvious. The only way you will determine this is by going through the relevant algebra. Now finally, let's ask ourselves, okay, you've done the easy ones, you've done y, the output. What happens if you wanted something like this signal f, which is inside that inner loop? Well, actually it's not so bad, because what I will do is I will first identify u, which is outside that loop. So I know that u equals m over, and I'm going to have to remember this from the previous slide, so you've then got 1 plus m into g over 1 plus gh into r, which gives me m into 1 plus GH over 1 plus GH plus mg into R. So I've identified the signal U. Now, what's the dependence of the signal F on the signal U? Well, now you can treat U as being an input to a separate loop. So I'll put this loop here in this blue line. And that's a standard loop which we've covered in previous videos. So I can write down F equals 1 over 1 plus GH into U. Well, I've got U because I've just solved that above. So therefore I can write 1 over 1 plus GH into M, 1 plus GH over 1 plus GH plus mg into R. And the bright ones among you will have spotted straight away that there's a cancellation here, and so you end up with M over 1 plus GH plus mg into R. So in summary, where a loop has multiple feedback paths, it may still be possible to define transferences between a loop input and an internal signal very quickly. So the main strategy is to redraw the block diagram, grouping together blocks where possible in order to simplify the overall structure. Once you've simplified the structure, then the shortcut rule of forward path over 1 plus loop transfer function is often good enough. Now, if this isn't good enough, it's not really working, then you're going to need more advanced shortcuts and rules which are not covered in this video, and you may need to look those up.